Mm, Hello everyone. So this is week 8, week 9 of the NPTEL course Introduction to Robotics, and this is the NPTEL problem solving sessions that I held weekly. So in this week, you guys have learnt about probability and then state estimation, like very rudimentary, ba basic state estimation using probability, specifically Bayes theorem. So what we'll do in this session is that we'll just take up a very simple problem, and if time permits, we'll take up another problem. I'll discuss these problems here in this session, and then if anybody joins in this session, then we can, just take up some questions. So yeah, so I think you guys might be very familiar with this problem here, okay, because this problem is very similar to what you were taught in the lectures. Okay, so this is the same problem. Okay, that there is a door. Okay, and the robot wants to know, there is a robot here. Okay, and it wants to know if this door is open or not. Okay, and how it can tell if it's open or not is by checking, okay, manually, if the door is open or not. And how does it check if the door is open or not? It pushes. Okay, so that is what we have been given here. It can push to open. Okay, it can try to push the door. Okay, and when it pushes the door, if it is open already, okay, then of course it will remain open. Okay, if it when it pushes the door, if the door is already open, of course it cannot get closed. That is why we have the probability 0 here. Okay, if the door is shut and it pushes the door, okay, then the door might open or might not open, okay, depending on how it pushes the door. So, okay, so there is a probability of 0.7, okay, that if the door is closed or shut initially and the robot pushes the door, then the door becomes open then, okay, and then if it pushes the door and the door is shut, then there is a 0.3 probability then that it remains shut, okay. So this is what we call our transition model, okay, or you know, you can call it your system model or anything. So basically, it tells you that you know, uh, given previous states, if we denote states by x, given x of t minus 1, okay, what is the probability of x of t? Okay, given x of t minus 1 and your action at this time instant, okay, what is this? Okay, so a transition model provides you with this information. Okay, and what do you do with this information? Basically, initially you have some beliefs. Beliefs are basically a probability. Okay, your probability of a variable, and here your variable is, you know, it's a Boolean variable. Okay, that tells you if the door is open or not. Okay, and this we are denoting by x0. Okay, so okay, so what you do with this with the beliefs is basically these are a probability that the variable has, you know, if let us say we allow it to have states 1 or 0, okay, or in this case we are allowing it to have states open or shut, okay. So what is the probability for it to have one state? Okay, that is your first belief. Okay. Oh, shit. And then what is the probability of it to have the second state? That is your, okay, that is what you call belief. Okay, this is the final probability of, your variable. Okay, so let us do one thing. Okay, in this question we consider that initially the robot has done nothing. Okay, and here you will see that we have a transition model when robot actually pushes the door. Okay, but we do not have a transition model when the robot does nothing. Okay, so you guys already know what the transition model is when the robot does nothing. uh, I mean, you saw it in the lectures also. Okay, that basically the states do not change. Okay, so xt given, okay, if ut do nothing, if I represent by d, okay, and xt minus 1. Okay, let us say that this is that x of t is open and x of t minus 1 is open. Okay, if it is open and we do nothing, it should be open. Okay, so similarly, if it is shut, okay, if it is shut and we do nothing, okay, and previously if it was open, okay, so previously if it was open and we do nothing, then what is the probability that it will be shut? It is 0 because we are actually doing nothing. So you will see that this, okay, if x of t is 0 given, okay, if it was initially shut, okay, if it was initially shut, then there is no way that now it can be open when the robot does nothing. Okay, this is important. Okay, and the probability that it is shut given that you do nothing and it was previously shut. Okay, so that is basically same. Okay, so now you have both of your transition models. So for this case that I'm telling you, that the robot does nothing, okay, but using its sensors, it measures, okay, that the door is open. Okay, so what we want to know is we want to know the updated belief. Okay, we want the updated belief, not BET, of course. Yeah, we want the updated belief that, you know, whether your door is closed or not. Okay, so we want for both open or shut. Okay, so x node is given to be 0.5. Okay, let us say we want after one time step. Okay, so what are these? Okay, so as we know, the algorithm for, you know, the Bayes algorithm. Okay, what is the first step in it? It is the prediction step. Okay, that you predict the next state. Okay, you predict the next state given your previous state and your interaction with the your model, okay, or the robot environment, interaction of the robot with the environment. Okay, so how do we do that? We write the predicted value, let us say as, okay, we represent it as bell bar for now. Okay, and we call it as O for open. Okay, so let us say this is O1. Okay, so this, according to Bayes rule, should be what? Probability that, you know, The new ones are 0, given that you have done nothing. Okay, for all the previous states, right? Okay, for all x of t minus 1. Okay, so for our case, okay, we only have two previous states. Okay, either it was previously open or closed, and we know that previously, okay, if I say it O of 0, okay, so this was given to me as 0.5 and S of 0, I'll call it S. Okay, shut for S, O for open. That is also 0.5. Okay, so I want the probability that the door was open, when we do nothing, that the door is open now when we did nothing, and previously it was open. Okay, we do this. Probability that now it is open, given you did nothing, when previously it was open, times, what is your current, what was the previous belief. Okay, so this, and what is the second possible state? That previously it was shut. Okay, this is not P, this is D. This is denoting that we are doing nothing, is equal to shut times previous belief that it was shut. Okay, so what will it come out to be? We know from our this do nothing transition model, okay, that this term, okay, here is 1, and this term, okay, here is 0. Okay, so it becomes 1 multiplied by 0.5 plus 0 multiplied by 0.5. Okay, so it is 0.5. Okay, so similarly, when you calculate for the probability that yes, if previously it was whatever it was, now if it is shut, okay, so this probability again similarly will be given by this formula, but here rather than taking O, we'll take shut case. Okay, so in that case also, okay, we will get 0.5. Okay, so this is your prediction step. You're predicting, given the model, okay, that what will be the next step, what is the probability, okay, that at the next step the state will be either O or S. Okay, but again we have sensors. Okay, so I will just write the beliefs, okay, the updated beliefs here. So O1, okay, it remains the same. Okay, and similarly for O2, okay, this also remains the same. But now we had said that your sensor reports that it is open. Okay, so now your updated belief after the measurement. Okay, so once you have predicted and now you're correcting that prediction. Okay, so second is the correction step. Okay, correction or measurement, you can say anything, that you are incorporating your measurement into your you know beliefs. Okay, so you correct the prediction from your measurement. And how do you do that? From your lectures, you know that. Okay, that your since your measurement is open, okay, because we are seeing that it is open here. Given that, what should we take? XTS open. Okay, because we are trying to get data or the updated belief about the open case. Okay, that we had predicted, if we had predicted that it was open, okay, okay, this is our prediction, except t, not t minus 1. If we had predicted that it was open, what is the probability that the sensor actually reports that it was open, right? And this neta is a scaling parameter. Basically, your 1 over neta is the total probability. Okay, that we'll calculate afterwards. So neta times, what is the probability that it reports open when you have predicted open? Okay, it is 0.8. 0.8 times what is the predicted belief? Okay, so that is your 0.5. Okay, so it comes out to be 0.4 times neta. Okay, and similarly for the shut case. Okay, so neta scaling parameter, this is scaling parameter neta is same when you are, just updating or calculating beliefs for the same variable or the same state. And here, or same set of states. And here your state is x naught. That is your, that shows, that tells you if the door is open or not. Okay, so that's why this neta is same. Okay, this will be your, that GT is, your sensor reports, because your sensor has reported that it is open. So you're now trying to, you know, get a probability that what should have been my state, okay, if my sensor had reported it to be open. What is the most likely state it could be? Okay, so this is neta times what is the probability of the sensor reporting open when it was, when you had predicted shut. Okay, if it was actually shut. Okay, not predicted, if it was actually shut. Okay, then you see that here it is 0.1 times 0.5. Okay, so this turns out to be neta times 0.05. Okay, so now just the final step to get the numerical values of belief, you want to get the value of the scaling parameter neta. Okay, so from the law of probability, you know that the net probability of any state should be 1. Okay, so what is the net probability here? Okay, either the door can be open or it can be shut. Okay, so it is 0.4 neta plus 0.05 neta. Okay, and that should be equal to 1. So this gives us that neta should be equal to 1 over 0.45. Okay, so now finally you have your updated beliefs after the measurement. Okay, first you had after the prediction, and then you have after the correction or the measurement. Okay, that is 0.4 divided by 0.45. Okay, and if it is shut, that is 0.05 divided by 0.45. So yeah, so we'll just quickly calculate the values. Okay, so 0.4, 0. Okay, so this probability comes out to be now 0.88. Okay, and now you need, like, that it to have, to satisfy the law of probability, that total probability should be 1. Okay, it will come out to be, okay, you can check this from your calculators also. Okay, so these are the updated beliefs when the sensor had reported that the door was open. Okay, so now you see that previously, we had a belief that, you know, the door was open. Okay, it was 0.5. Okay, then your sensor told you that it is indeed open. Okay, so now your belief that the door is open, okay, it has gone up. Okay, you are more confident in your reporting, or basically, so you're more confident in your probability that yes, the door indeed is open. Okay, because your probability, basically, or your belief that the door is shut has now dropped from the same 0.5 to 0.12. Okay, so after one measurement, okay, now we are pretty sure that yes, the door might be open. Okay, and there is a very less probability that the door is closed. Okay, but you see, there is still probability that the door is closed, and that will always be there in case of probabilities. No probability, can be zero if it is non-zero at some point of time. Okay, so now since we have, you know, done this case when you do nothing, okay, and the sensor reports it to be open. Okay, so now what we will do is, after we have taken a measurement without doing anything, we will take a measurement. Let us assume that we take a measurement when we push the door. Okay, now again, we are talking about what, your sensors. Okay, the data that you will record from the sensor. Okay, so we'll have to make it up. Okay, of course, because in real life you will get the sensor data from, of course, your sensor. Okay, so now what I'm saying is that, okay, let us first write our updated beliefs here. Okay, our updated belief that the door is open is 0.88, and our updated belief that the door is shut is now 0.12. And now I'm saying that, okay, you have pushed to check. Okay, so basically now you will use this transition model. Previously we had used this transition model when we said that the robot had done nothing. Okay, now we are saying that the robot has pushed to check if it is open or not. Okay, so now we'll use this transition model to get our prediction. Okay, because we use a transition model to to get predictions. Okay, and now let us assume. Okay, okay, let us say that this is your U2. Okay, this was your O1, this one. Okay, wait. Hello, Mukund, can you hear me? Okay. So whatever what I had did till now is that I had taken an example problem. I think you might have seen this problem also. But what change I've done here is that I have assumed that the sensor had reported that the door was open instead of, that the door is shut that you have been given in your assignment. Okay. So for that, I had gone over if the robot does nothing, then using the transition model of doing nothing, okay, how do we get the updated beliefs, okay, of the door being open and the door being shut. Okay, so now we are taking another case that now the robot has actually tried to push the door. Okay, and the sensor, now it has, the sensor has told you that the door is actually shut. Okay, so now I just want to know that what is the new probability after these two actions. Okay, basically, what is your probability belief that the door is open at the second step, and the belief that this door is shut at the second step. Okay, so again, our first step is the prediction step. Okay, so how do we do prediction? Okay, so I write this bell bar as your predicted. Okay, bell. Okay, so you want to know that if this was open, okay, if it should be open, given that you tried push to open, okay, and you previously were open, okay, this multiplied with belief that it was open, okay, the last belief, your most recent belief, okay, and again you want to, because you want to know the prediction for the door being open, okay, so that is why you're calculating the probability, total probability for the door being open, okay, so if it was pushed and if it was shut before, okay, and the multiplied with the belief that it was shut before, okay, so what will be the numbers here? Okay, so we want this and this, right? 1 and zero point 0.7. Okay, so the probability that the door is open when you have checked it is open, it is 1. Okay, and your probability, your belief that the door is open right now is 0.88 plus the probability that the door is, you know, will be open when you have pushed to check. Okay, if it was closed before, okay, that is given as 0.7. Okay, so what do we get here? 0.7. Okay, so we get so there is a very high chance, okay, that if you have pushed, that the door will be open. Okay, there is a very high chance. Okay, and now similarly we get the prediction that what are the chances that the door will be closed after, even after you're pushed. Okay, you're pushed to open, okay, and previously it was shut, okay, in this case. Okay, so what I will also take belief that it was shut, okay, plus probability that now it is shut even if you had pushed to open, given that it was open before, okay, times belief that it was open before. Okay, so what will this come out to be? Okay, okay, so probability of being shut when it was shut earlier and we had pushed to open is 0.3, right? And the probability of it being shut when it was open before, it is 0. Okay, and that makes sense actually. If it was open before and you have pushed to open, then it should remain open. Okay, there is no way it can be shut. Okay, so what do we have here? This was your 0.3. Okay, that you have tried to open the door and it was previously shut and it is still shut. Okay, so this is 0.12 plus 0 times 0.88. Okay, so what will this come out to be? Let us write it here. So 0.3 times 0.12. Okay, so now this is 0.036, a very low chance that the door will be shut even in the next, you know, even after you have tried to push it open. Okay, but now I'm saying that the sensor reports that it is shut. Okay, okay, so now after you have your sensor, sense measurement basically, that is when you apply your correction or measurement update. Okay, you can call it any of the two, either measurement update or correction step. Okay, and for the measurement step or the correction step, we know that, okay, it is the base probability that you have, done, saw in the lectures also, and you might have done in the third. So this neta is just a scaling parameter. Okay, that is, 1 over the total probability. Okay, for belief of x naught. X naught is your state that tells you if it is open or not. Okay, so this is just a scaling parameter. Okay, so now we take the measurement model, that what is the probability that your sensor actually reports shut, because it has reported, when it is actually open, right? If it was actually open and the sensor had reported it to be shut. Okay, so, and this multiplied by what is your current prediction, okay, that your door is open. Okay, so this is what gives you your updated or the corrected belief. Okay, uh, corrected you use when you are very sure that whatever your sensor is giving, okay, is correct. Okay, so basically, in that in that sense, you are correcting your prediction. Okay, but there can be cases where your sensor can give you wrong values. Okay, for example, this is very likely in this case that, whatever the sensor had reported, it was wrong. Okay, because you see, we have a non-zero probability here, that even if the door was open, the sensor can report it to be shut, and likewise, even if it was shut, the sensor can report it to be open. Okay, so what we get here is times what is the probability that the sensor reports it to be shut, when it is actually open. So reports it to be shut when it is actually open, that is 0.2. 0.2 multiplied by what was the belief that the, you know your this update predicted belief for the door to be open, that is 0.964. 964. Okay, so this comes out to be 964. Okay, so now this is neta times 0. Okay, so this is times 0.1928. Okay, just keep it in your mind that we cannot comment on the probability right now, because there is a scaling parameter neta, and what we do not know what is the value of neta. Okay, we'll calculate it afterwards. Okay, how will we calculate? We'll use the total probability. Okay, that this total probability should be 1. Okay, I'll show you how to do that. Okay, and since these are the probabilities for the same, okay, the door can either be open or be closed. Okay, so this is the same scaling parameter, but now, you know you take the probability that the sensor is reported shut when it was actually shut. Oh, not O2. Okay, the prediction that it was shut. Okay, so what is it? It is 0.9. Okay, so sensor is fairly confident. Okay, not our sensor. We are fairly confident, as given in our model, that if the door is shut, there is a very high chance that the sensor will also report that it is shut. Okay, so it is neta times 0.9 times what your predicted belief that the door was that the door has to be shut, if your robot tried to open it. Okay, and this will come out to be 0, okay, as your 0.0324. I'll just admit this guy. Yeah. Okay, so now once you have, okay, so basically these, okay, this times neta. Okay, so once you have these are your updated beliefs. Okay, after your robot has interacted and you have also incorporated the sensor values. Okay, but how do you get the value of this variable neta? Okay, so you can see that these are the probabilities for the same variable either being open or being shut. Okay, so we know that the total probability, okay, of any variable, it should be 1. Okay, so in this case also, the total probability, okay, that the belief that either the door is open or that the door is closed or shut, it has to be equal to 1. Okay, because there is no other possibility. Okay, so this comes out to be your neta times 0.1928 plus 0.0324 equal to 1. Okay, so this gives us neta is equal to 1 over, right, 0.0324, 0.2252. Okay, so after this you can just replace the value of neta in these expressions and get the final probabilities. 1928 divided by 0.2252. Okay, so now after this, after this prediction step, the probability that the door is open, okay, that is 0.856. Okay, and the probability that the door is closed, okay, it is divided by 0.225, 0.144. Okay, now I want you guys to see something. Okay, so initially we were given, okay, that the probability was 0.5. Okay, that the door can either be closed or be shut. Okay, we don't know. Okay, so after this we said that the robot has done nothing. Okay, but the sensor, okay, let us call it U1, the sensor has reported it to be open. Okay, so given our transition model and our measurement model, okay, this is your, okay, we had gotten our beliefs as 0.88 and 0.12. Okay, that when the robot has not interacted and your sensor has told you that it is open, okay, then you are pretty sure that the door is actually open. But after this, okay, what I told you was that the robot has now tried to push it open and the sensor has reported that it is shut. Okay, after that, your belief that the door is open, it has actually dropped 0.856. Okay, and your belief probability that the sensor is that the door is actually shut, it has increased. Okay, but it has not increased by much. Oh, basically it is this has not decreased by much and this has not increased by much. Okay, why? Because you see in your models, okay, your uh, you're very sure, your model makes sure that if the robot tries to push it open, okay, then it will become open. Okay, then it will open the door. Okay, because there is a very high probability in both the case, even if it was initially open or if it was initially shut. Okay, so that is why even if your sensor has reported that yes, it is shut, okay, yeah, still the probability that the door is open right now, okay, that is high. Okay, but due to the fact that you have your sensor had reported that it is shut, it has decreased from what it was previously. Okay, so now in this case, okay, what you would want to do in a practical scenario, okay, we say that when the belief of robot, okay, basically the probability that the door is actually open, okay, because let's say you want the robot to go through the door, okay, when it is greater than equal to 0.99, okay, that is when you say, okay, to the robot that go through, okay, go through the door, okay. So to get to a belief of 0.99, you will have to take multiple such measurements and multiple such actions, okay. Again, let us say that the robot was actually closing the door, okay, then, okay, you would say that when the door is actually closed, when you're very sure that the door is closed, then you go away, okay. So this is how you use your, you know, state estimation, basically the probability of your states to guide your actions, okay, guide the behavior of the robot, okay. So I think this was the this should help you in your assignments also, and if you know, try to advance, try to implement something in robotics, basically state estimation. So are there any doubts that you guys have, Kirtana and Shajin? If not, then I will be ending this session. Like, you can ask any doubts if you have.
Sir,
Yeah.
just for this guidance in proceeding with the course, after this introduction to robotics course,
Hmm.
which upcoming course will help me to advance well in the robotics topic,
Okay, so
especially from NPTEL?
yeah, I think NPTEL has like many courses. So I think you should find some course that is on robot navigation.
Okay.
Okay, because
So,
in this course, yeah,
yes, sir,
in
you
the,
may continue.
yeah. So what I was saying is that in this course, you have learned how, how you model the robots, how you control the robots, okay, and how you get the robot to know where it is, okay, because you will be studying a bit of SLAM also. But after knowing all this, how do you plan your path? Okay, how do you plan that if the robot is at a given state, how does it reach the next state? Okay, so that is what your navigation is. So look for some courses on navigation, and look for some courses on, some algorithms also, okay, because there will be some algorithms on in the navigation course, but you should be able to implement those algorithms also, okay. So some basic courses, that gives you exposure to programming, okay, because programming is very important when you are trying to interact with robots. Does that answer your question?
Yes, sir.
Okay, so yeah, bottom line, just look for a course on robot navigation. That should be your next step.
Okay, got it, sir. Thank you.
Okay, okay, so I think there are no more doubts. Do you have any other doubt, Kitana?
No, sir.
Okay, then I will end this meeting and you guys can leave. Thank you for attending.
Thank you, sir.